Voyager 1 is still moving away from the Sun. The question is how far it can travel after the mission itself has gone silent. That difference matters. A spacecraft can keep moving long after it can no longer send data. It can cross distances no human machine has crossed while becoming scientifically unreachable. The body survives, the voice fades first. So Voyager 1 is not only a story about distance, it becomes a story about power, signal, time, and what exploration becomes when communication ends. The tempting answer is to imagine the spacecraft traveling forever. In a simple sense, it may, but the useful answer is harder. We are going to follow Voyager 1 across that full chain of limits, from the signal we still receive to the distances where the spacecraft becomes silent. By the end of this video, you will understand where Voyager's mission ends and where the object keeps traveling without us. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. Voyager 1 is easy to remember as a spacecraft from the past. The famous photographs, the outer planets, and the old mission dates make it feel like an artifact from a finished age. But the title question does not begin in 1977. It begins now, with a machine that has already done its historic work and is still moving. Now picture the spacecraft without the museum light around it. A bus-sized machine, a dish antenna, long booms, aging electronics, and a power source that has been fading for decades. Earth is not close behind it. NASA and JPL described Voyager 1 in 2025 as more than 15 billion miles, or 25 billion kilometers away. A radio signal from Earth took more than 23 hours to reach it. By the time a command arrives, the people who sent it have already lived through most of another day, but that distance can trick us. More than 15 billion miles feels like a final number. It sounds as if the spacecraft must already be almost gone from the solar system in every possible sense, and compared with the orbit of Neptune, it is incredibly far. Compared with the Oort Cloud, nearby stars and the moving galaxy, it's still close to the beginning. We have to hold both truths at once. Voyager 1 is the farthest human-made object, also nowhere near another star. It becomes already in interstellar space, as NASA defines the space beyond a heliopause. Also not necessarily beyond the Sun's widest distant architecture, if we count the inferred Comet Cloud that may extend tens of thousands of astronomical units from the Sun. So the simple map breaks immediately. The spacecraft can be record-breaking and still early in its larger journey. It can be far beyond the planets and still not finished with the Sun. It can be almost a light day from Earth and still light years from anything we would call a destination. Here is the first clean answer. Voyager 1 is not traveling because its engines are pushing it every second. It's traveling because gravity gave it a path and nothing has stopped it. After its planetary encounters, the spacecraft was sent onto an escape trajectory from the Sun. Unless a major future disturbance changes that path, it keeps moving. That matters because many ordinary machines stop when their mission ends. A car runs out of fuel and sits beside the road. An aircraft lands. A ship reaches harbor. Voyager is different. When the mission narrows, the object does not park. When an instrument shuts down, the body of the spacecraft continues outward. When the last signal eventually fails, the trajectory remains. But we should not rush past the living machine. Voyager 1 is not only a symbol. NASA's public mission material still describes both Voyagers as continuing their journeys in interstellar space. The live position table has also required careful updating as Voyager approaches one light day from Earth. That's exactly why we should avoid pretending the current distance is a fixed statue. It changes every day. What does not change is the scale of the situation. Voyager 1 is already so far away that communication feels like archaeology in real time. Engineers send a command into darkness. The spacecraft receives it many hours later. If it answers, the answer begins its own long return. A simple round trip approaches 2 days, and yet the spacecraft itself experiences no drama in that delay. It does not wait in a narrative sense, it moves. Every second it adds more distance from the Sun. Every day it carries the human object farther into a region no earlier spacecraft had measured from inside. Here's why the video cannot be a tracker update. A tracker tells us where Voyager is today. The deeper question asks what kind of thing Voyager becomes tomorrow, next century, and far beyond the time when anyone can command it. We also have to keep its old story in the background. Voyager 1's Jupiter and Saturn flybys explain how it reached this outbound path. They do not own this question. The Grand Tour belongs to another story. Here the famous mission is already behind us. The machine has become a test of what travel means after the heroic part is over. Pause on that for a second. The public memory of Voyager is filled with images. The present Voyager sends no new pictures. Its cameras were turned off long ago. The spacecraft that remains is quieter, narrower, more mathematical. Magnetic fields, plasma waves, carrier tones, housekeeping data. A signal so faint that Earth needs giant listening systems to keep the relationship alive. But narrower does not mean irrelevant. In some ways, this is the sharper version of Voyager. Stripped of planets and spectacle, it forces a cleaner question. How far can a machine go once its famous work is finished? How long can it remain a spacecraft rather than a relic? And when it finally becomes a relic, does its journey become less real? We can already see the ladder forming. There's Voyager as a living spacecraft. There's Voyager as a communicating spacecraft. There's Voyager as a silent object. There's Voyager beyond the Sun's wind. There's Voyager still inside or not yet beyond the Sun's possible Comet Cloud. There's Voyager passing near a moving star without arriving. There's Voyager in galactic motion, long after human schedules have stopped making sense. The first part of the answer is almost paradoxical. Voyager 1 is unimaginably far, and it is not very far at all. That's not a trick. It's what happens when a human-scale question touches astronomical scale. So before we ask for a final distance, we need to decide what kind of travel we are counting. Now hold the spacecraft against another scale. Neptune is roughly 30 astronomical units from the Sun. Voyager is far beyond that familiar planetary distance, but the inner Oort Cloud may begin thousands of astronomical units away. That means the spacecraft has already outrun the planets and still has an immense solar neighborhood ahead of it. Here's the kind of scale that makes ordinary language fail. We say outside as if it means one border. We say far as if the word is finished after one comparison. Voyager keeps showing us that every distance needs a reference point. Far from Earth is not far from the nearest star. Far beyond Neptune is not beyond the Oort Cloud. Beyond the heliopause is not automatically beyond every useful solar system boundary. And that is why the object itself has to stay at the center. If the answer becomes only numbers, we lose the human-made machine that makes the numbers matter. If it becomes only emotion, we lose the physics that makes the journey real. Voyager 1 is the bridge between those two ways of thinking, a built object, still outbound, forcing us to translate scale into meaning. The word travel sounds simple because we use it for human things. We travel when we drive across a city, fly across an ocean, or walk from one room to another. Movement, purpose, and arrival usually stay tied together. Something goes somewhere, and the story ends when it gets there. But Voyager 1 breaks that pattern. Now look at the spacecraft as a machine in deep space. It has no road under it. It has no destination sign ahead. It isn't burning engines in a steady push toward a target. Its future is not a trip itinerary. The spacecraft is moving because it already has velocity relative to the Sun, and because empty space offers almost nothing like friction to slow it down. So when we ask how far it can travel, we are asking several questions at once. One version asks how far Voyager can travel as a controlled mission. That means engineers can send commands, the spacecraft can respond, critical systems remain alive, and the machine is still under some practical human care. Under that definition, power and health are the limits. Another version asks how far Voyager can travel as a science platform. That's narrower. A spacecraft might still be alive, but if the instruments that return useful science are off, the meaning changes. Voyager 1 has already crossed far into this narrowing. Most of its original instruments are silent. The present mission depends on the few that remain. A third version asks how far Voyager can travel as a communicating spacecraft. That definition is different again. Maybe the science is reduced, maybe the data rate is tiny, but if Earth can still hear a carrier signal, if engineers can still receive enough information to know the spacecraft is there, then the relationship has not ended, and then we can ask the hardest version. How far can Voyager 1 travel as a silent artifact? That version does not care whether a receiver on Earth can hear it. It does not care whether an instrument is warm. It asks only what happens to the physical object. Under that definition, the answer stretches far beyond the mission. Here is where the question becomes powerful. A dead spacecraft is not a stopped spacecraft. A silent spacecraft is not a missing spacecraft in the physical sense. It may be lost to communication, lost to control, and lost to science, while still following a real path through space. But we need more rungs. Voyager 1 is already beyond the heliopause, which means beyond the sun's wind bubble. That's one kind of boundary. NASA calls this interstellar space. It becomes a real scientific crossing. It changed what Voyager was measuring around itself, but another boundary waits much farther out. The Oort Cloud, if we count it as part of the solar system, pushes the edge into deep time. It isn't a wall, it becomes an inferred, diffuse reservoir of icy bodies, spread so widely that the word cloud almost feels too solid. If Voyager must pass through or beyond that outer region to leave the solar system in a broader sense, then the journey is measured in hundreds and tens of thousands of years. Then there is the star problem. Many people have heard that Voyager 1 will pass near Gliese 445, also called AC plus 793888, in about 40,000 years. That can sound like a destination. It isn't. The spacecraft will pass within about 1.7 light-years of that star. At that time, that star will be the nearer reference point than the Sun. But 1.7 light-years is still a vast miss. It's proximity on a galactic scale, not a rival. And after that, even the word near becomes slippery. The Sun moves. Gliese 445 moves. Voyager moves. Every star in the neighborhood is part of the Milky Way's wider motion. A future map cannot be treated like pins on a wall, so the ladder is not a dodge. It becomes the only honest way to answer the exact title. If someone gives one number, they have already chosen a definition, even if they do not say so. Let's say the question again in plain terms. How far can Voyager 1 travel as a spacecraft we can still use? Not as far as people imagine, because power is shrinking. How far can it travel as a signal source? Farther, if pointing and radio systems hold. How far can it travel as an object? Much farther than any mission clock. How far can it travel before leaving the Sun's larger neighborhood? Maybe tens of thousands of years. How far before it gets to another star? It does not reach one, at least not in the famous Gliese 445 event. How far in deep time? There may be no single destination to name. This structure also protects us from two bad answers. The first bad answer is too small. Voyager dies soon, so its journey ends soon. The second bad answer is too grand. Voyager is basically headed to the stars, so it has an obvious interstellar destiny. Both miss the point. The real answer sits between them. It's more disciplined than fantasy and stranger than a shutdown date. So we should treat the ladder as a listening tool. not a technical escape hatch. Each rung removes one kind of certainty and leaves another kind of motion behind. The operating mission may end, but the trajectory remains. The science return may narrow, but the signal may continue. The signal may disappear, but the object does not vanish from physics, and that is the shape of the whole question. We are going to move from the kind of travel humans can still participate in, to the kind we can only model. At each step, Voyager 1 becomes less available to us and more purely governed by space itself. That is not a failure of the answer. It is the answer becoming honest. Now that the ladder is clear, we can begin at the narrowest rung, the living spacecraft. Think of the ladder as a way of being fair to the viewer. A viewer who clicks the title deserves concrete answers, not a cloud of caveats. But the same viewer also deserves not to be tricked by a false single number. The ladder gives both, answer after answer, each one attached to the definition that makes it true. Here's how science often becomes clearer. We do not begin by making the world vaguer. We begin by separating things that everyday language has blended together. Alive is not the same as returning science. Returning science is not the same as sending any signal. Sending a signal is not the same as moving. Moving beyond the heliopause is not the same as clearing the Oort Cloud. Passing closer to a star than to the sun is not the same as arriving. Once those separations are in place, the title question becomes sharper than it sounded at first. It's no longer asking for a trivia fact. It becomes asking which meaning of travel survives after every easier meaning has fallen away. We have separated the first problem. Travel is not one thing. Voyager can move, communicate, return science, or merely persist, and each definition has a different limit. Now the open question becomes the closest one. How far can Voyager travel while it is still a working spacecraft rather than only a moving object? Let's slow down with that first living rung. Voyager 1 is not alive because every original system still works. It becomes alive because enough of the right systems still cooperate. That's a narrower, more fragile kind of life, and it matters for the title question. We are not asking whether the famous spacecraft of the planetary photographs still exists in its full old form. We are asking what remains useful now after nearly half a century of cold, distance, radiation, and careful engineering triage. NASA's instrument table gives the present shape of that survival. The magnetometer is still operating. The plasma wave subsystem is still operating. Those names can sound sterile, so translate them immediately. The magnetometer lets Voyager sense magnetic fields around it. The plasma wave instrument listens for waves in the charged particle environment. They are not cameras. They do not give us another postcard. They give us a way to read the invisible weather around a spacecraft beyond the sun's wind bubble. But look at what has gone quiet. The cosmic ray subsystem was turned off to save power. The low-energy charged particle instrument was turned off as the power budget tightened. The plasma instrument on Voyager 1 has been unusable since long before this final era. The imaging cameras and other planetary tour instruments belong to an earlier spacecraft identity. They helped make Voyager famous, but they do not define the machine we are asking about tonight. So when we say Voyager 1 is still operating, we have to hear the sentence honestly. It does not mean the spacecraft is fully healthy in the everyday sense. It means an old machine still has enough electrical power, thermal control, pointing, computer behavior, radio function, and surviving instrumentation to remain more than a silent object. And this is where the living spacecraft answer becomes useful. A probe does not need every instrument to stay a mission, but each lost instrument changes what kind of mission remains. The spacecraft can still be alive as an engineering system after its scientific senses have been reduced. It can still be scientifically meaningful after most of its old abilities are gone. It can still be commandable even when every command has to be chosen with the caution of someone touching a structure that cannot be repaired. Picture the engineering team facing a machine that cannot be visited. No technician can open a panel, no replacement part can be launched to it, no astronaut can tighten a connector or clean a sensor. Everything depends on inference from telemetry, on old documentation, on patient testing on Earth, and on commands sent into a delay that turns every intervention into a wager. So that is why the word living should not be romanticized. It isn't a creature moving through the dark. It becomes a system with enough remaining pathways to act, answer, measure, and survive. The romance is not that Voyager is magically alive. The deeper wonder is that the practical definition still holds at all. Now connect that back to distance. If Voyager moves about 17 kilometers each second relative to the Sun, then every year of continued operation adds a real distance to the living mission, but those yearly distances are tiny beside the next scales. A few more years of measurements matter enormously to heliophysics. They barely move the needle against the Oort Cloud. That contrast is the key. The Living Spacecraft answer is short on the map and precious in science, so the first rung is not a grand interstellar future. It becomes a careful present. Voyager 1 can travel as a living spacecraft only while a shrinking set of systems remains warm enough, powered enough, pointed enough, and coherent enough to keep the machine in conversation with Earth. When that condition fails, the physical object keeps moving, but this particular kind of travel ends. One more detail matters before we move on. The remaining instruments are not random leftovers. Magnetic fields and plasma waves are exactly the kinds of measurements that still make sense outside the heliosphere. Voyager is no longer a planetary camera platform. It becomes a probe embedded in a thin, electrically active environment between stars. The science has changed because the place has changed. That makes the narrowing less like decay and more like specialization forced by age. We should not pretend the losses are good. They are losses. But the instruments still on board answer questions that belong to the region Voyager now occupies. They help describe how the Sun's boundary gives way to the interstellar medium, how disturbances move through plasma, and how the spacecraft's surroundings differ from the planetary system it left behind. Now think about commandability as part of being alive. Voyager does not have to be clever in the modern autonomous sense. It has to remain predictable enough for humans to work with it. If engineers know what mode it is in, how it is oriented, what power it has, and how it responds to commands, then the mission still has a body. If those facts become unknowable, the same physical spacecraft becomes something else. So this rung is not only about whether a switch is on, it becomes about whether the machine still belongs to a living operational loop. Measure, report, command, adjust, survive. That loop is fragile, but while it exists, Voyager is not merely an artifact. It's still a working outpost at the edge of what the Sun can tell us directly. We also have to remember that every surviving measurement is rare. No fleet is lined up behind Voyager 1 at the same boundary, ready to replace it when it tires. A small amount of data from the right place can matter more than a flood of data from an easier place. So that is why the living rung deserves patience. Now let's narrow the first real limit. Voyager 1 is not alive the way a new spacecraft is alive. It becomes alive in a reduced, carefully protected sense. A few systems still matter enormously. Other systems have already gone dark. That difference is the first place where the title question becomes less like a distance counter and more like an engineering question. Think of the spacecraft as a house at the edge of a continent, with most of the rooms closed to save heat. The cameras are not waking up for a final look. The planetary tour instruments do not define the present mission. What remains is quieter. Magnetic field measurements, plasma wave measurements, the ability to point, listen, receive instructions, and send back a thin stream of information across a distance that already feels almost unreal. But that thin stream is not nothing. It becomes the difference between an object merely existing beyond the heliopause and a probe still participating in science. MAG and PWS being listed as operating means Voyager 1 can still describe parts of its environment. CRS and LECP being off means another layer of its scientific body has been sacrificed. PLS has been out of the Voyager 1 story for far longer. The spacecraft has not died all at once. It has become narrower, and that narrowing is the point. On Earth, we often imagine a machine has two states: working or broken, on or off, useful or finished. Voyager 1 refuses that neat division. It can be commendable while diminished. It can be scientifically valuable while incomplete. It can remain famous while doing work that is not visually dramatic. The cameras made the public fall in love with Voyager. The remaining instruments ask for a different kind of attention, so under the Living Spacecraft definition, distance is not just how many miles have accumulated since launch. Distance is what the machine can still do after those miles have made every repair impossible. A fault on a nearby satellite can sometimes be met with quick diagnostics, new commands, and a fast confirmation. A fault on Voyager becomes a conversation stretched over days. The team has to imagine the spacecraft's condition from telemetry, send a careful instruction into the dark, and wait while physics enforces the delay. That delay changes the emotional weight of every remaining function. A heater is not just a heater, it's protection for a component that may decide whether another measurement can happen. A bit of computer memory is not just a place to store numbers. It's part of a machine that has already outlived the world that built it. A stable attitude system is not just pointing hardware. It keeps Earth in the narrow geometry where communication is possible. Now notice what this does to the question. If we ask how far Voyager 1 can travel as a living spacecraft, the answer is short compared with the rest of the video. It's measured in the remaining years of power, thermal margin, fault protection, and commandability. It isn't measured in tens of thousands of years. It isn't measured by the next star. It belongs to the near future, and it may end while the physical object is still close to home on the galactic scale. That can sound disappointing until we hear the opposite truth. The living spacecraft answer is short because it is intimate. It belongs to human engineering. People still decide what to preserve. People still interpret the telemetry. People still choose which scientific sense the spacecraft gets to keep for a little longer. The machine is far away, but this rung still has a human hand on it through radio. And when that hand can no longer make contact, Voyager does not stop. It changes category. So that is why the living spacecraft deserves its own answer. It becomes the last phase where the journey is still shared in something like real time, however slowly. After that, Voyager can remain an outbound object, but the working mission has ended. The simplest, honest sentence is this: as a living spacecraft, Voyager 1 travels only as far as its remaining systems can keep it operating and meaningful. That limit comes long before the larger journey ends. Now the living rung meets its most stubborn number. Watts. Now we can place the next piece. The strange thing about Voyager's near future is that the enemy is not a cliff in space. It isn't a border the spacecraft will hit. It isn't a distance where physics suddenly refuses to let radio waves pass. The first hard limit is smaller and quieter. It becomes a power supply that loses output year after year, while the list of things needing power refuses to become zero. But we need the next constraint. The Voyagers use radioisotope thermoelectric generators. That phrase can sound like a machine room label, but the idea is plain. Plutonium produces heat as it decays. The spacecraft converts some of that heat into electricity. No sunlight is doing the work out there in any useful way. The sun is too distant for Voyager to behave like a solar-powered probe. It carries its own fading heat source. NASA and JPL describe the decline as about 4 watts of power each year. On Earth, 4 watts can feel almost comic. A small night light, a modest device on a desk, a number too small to sound cosmic. But Voyager is not a kitchen counter. It becomes an old spacecraft living on a shrinking budget, and the budget has already been cut for decades, so we should hear 4 watts as a decision. It can mean a heater. It can mean part of an instrument's future. It can mean margin for a subsystem that keeps another subsystem alive. It can mean whether the spacecraft has enough flexibility to ride through an anomaly without forcing a larger sacrifice. Here's why instrument shutdowns should be heard as strategy, not simple loss. Turning something off is painful because the mission becomes narrower, but it can also preserve the spacecraft's ability to keep doing anything at all. Engineers are not casually removing capabilities, they are buying time with pieces of the machine, and the purchases get harder. Early in a long mission, a system may be shut down because its main job is complete. Late in the mission, a shutdown can feel different. It's no longer just mission design, it's survival arithmetic. The fewer active systems remain, the less room there is to trade one for another without changing the identity of the mission. Think of the difference between a bright house and a winter cabin. In a bright house, turning off one lamp changes little. In a winter cabin with one weak stove, every choice is about staying alive. Voyager is closer to the cabin. The heaters, the radio, the command system, the attitude control, and the remaining instruments all compete for a shrinking flow of energy. Now listen to the 2030s caveat carefully. NASA and JPL have described the possibility that at least one science instrument could continue operating into the 2030s if the spacecraft remains healthy and if engineering margins hold. That's not a promise carved into a calendar. It's conditional. A fault could force a different choice. A successful workaround could preserve one function longer than expected. The date is a hope bounded by hardware, not a prophecy. This matters because countdown thinking flattens the story. A neat final date would make Voyager feel like a clock running down to a dramatic last second. The real engineering story is more granular. It becomes a sequence of thresholds. First one instrument, then another, then perhaps science without much redundancy, then perhaps a carrier signal without meaningful science, then silence. Not a single fall, a narrowing corridor. So under the power definition, Voyager's travel is limited by energy before it is limited by space. It can keep moving without useful power, but it cannot keep being a living spacecraft without it. The outer solar system may stretch for thousands of astronomical units. The power margin is measured inside the body of the machine. That contrast gives the title its first severe answer. Voyager 1 can travel only a small additional distance as an actively powered science platform compared with the distances still ahead. The object may cross immense future regions. The powered mission cannot follow it indefinitely. 4 watts a year is small on Earth. In interstellar space, it is the sound of the first answer closing. There's another reason 4 watts is more severe than it sounds. The power system does not decline in isolation. The spacecraft also ages. Electronics can become less forgiving. Thermal behavior can matter more. A component that once had comfortable margin may now need protection just to remain stable. So the same annual loss can hurt more late in the mission than it would have hurt early on. Here's why the team cannot rank instruments by public popularity. A camera would be emotionally satisfying, but it is not the right use of energy in this era. A less glamorous subsystem may be essential because it keeps the spacecraft pointed, warm, timed, or understandable. The mission's public identity and its survival needs are no longer the same thing. The power budget also links every rung together. Without enough power, science ends. Without enough power, communication ends. Without enough power, attitude control and fault protection become harder. The wattage is not a side issue before the real deep time story. It becomes the gate through which all remaining active definitions have to pass, and because the spacecraft cannot be refueled, every choice is irreversible in a practical sense. A shutdown may preserve life, but it also closes a door. Engineers can sometimes recover functions or change strategies, but the long trend cannot be negotiated away. Plutonium decay is not a management problem that can be solved. It becomes a physical clock that can only be stretched by using less. And using less is not the same as doing nothing. A leaner spacecraft still needs planning. It needs schedules, safe modes, communication windows, and decisions about which risk is acceptable. The mission survives not because the problem is small, but because engineers keep converting a shrinking supply into one more workable season. Now let's look at the quiet subtraction behind that limit. 4 watts per year does not sound dramatic. It sounds like a number too small to carry a documentary. On a kitchen counter, 4 watts is the difference between a tiny lamp and darkness. In a deep space probe with almost no spare margin left, 4 watts is a set of choices. Voyager 1 is not powered by sunlight in any practical way now. The sun is too far behind it. The spacecraft depends on radioisotope power, electricity drawn from heat released by decaying plutonium. That design was one reason the mission could keep going far beyond the giant planets. It gave Voyager a slow-burning source of energy for places where solar panels would fade into symbolism. But decay is a one-way bargain. The heat falls. The conversion to electricity yields less. Engineers can manage the decline, but they cannot refuel it. They can turn something off, change a duty cycle, adjust operations, or accept more risk. They cannot make the power source young again, so each shutdown is not just a loss, it becomes a purchase. Turning off one instrument may buy time for another. Reducing one demand may protect communication. Preserving a heater may matter more than keeping a sensor awake. The public sees a list of instruments. The mission team sees a survival budget. Here's where the story becomes almost painfully practical. Voyager 1 is not facing a wall in space. Nothing ahead says stop. The limit is inside the spacecraft. It's in the electrical margin, the thermal balance, the ability of old electronics to keep behaving, and the number of compromises still left before the compromises become the mission. We should be careful with dates here. The 2030s are not a promised finish line. NASA and JPL have described a conditional hope that at least one science instrument may keep operating into that period if the spacecraft remains healthy enough and if the engineering trade-offs keep working. That's very different from saying Voyager has a scheduled end. A sudden fault could shorten the story. A clever recovery could extend one part of it. The future is managed, not guaranteed, and that managed uncertainty is more interesting than a countdown clock. A countdown clock would make the audience wait for one dramatic zero. Voyager's power problem asks us to watch a living system become simpler. Not dead, then alive. Not whole, then gone. Simpler, colder, less redundant, more dependent on every surviving part, doing exactly enough. Think about what power means here. It isn't only electricity for science, it's electricity for communication. It's warmth where warmth prevents failure. It's orientation, memory, fault protection, and timing. A spacecraft without enough power may still be physically intact. It may still be racing away from the sun. But the mission, as an active relationship with Earth, becomes thinner every time the budget shrinks. Now the title question has a near-term answer. How far can Voyager 1 travel while it remains a powered science platform? Only as far as the remaining watts allow. That answer may be tiny beside the Oort Cloud. It may be tiny beside 40,000 years. Yet it matters because it is the last distance over which Voyager can still report something fresh about where it is. There's a kind of humility in that. The most famous outbound spacecraft humans have ever made is being governed by numbers smaller than household appliances. The scale outside is immense. The margin inside is small. That contrast is the drama. A machine moving through interstellar space is also a machine asking whether one more instrument can be kept warm, one more transmitter session can be supported, one more careful command can be worth the energy it costs. So the power rung answers the title with a hard constraint. Voyager can travel as a working science machine until declining radioisotope output and spacecraft health no longer support that role. After that, the object continues outward, but the powered mission has yielded to the next meaning of travel. Now separate the machine from the relationship. A spacecraft can have power and still fail to be heard. It can be moving perfectly and still become unreachable. Communication is not a substance stored inside Voyager. It becomes a chain stretched between the spacecraft and Earth, and every link has to keep holding. On Voyager's side, the requirements are unforgiving. The transmitter has to work. The high-gain antenna has to point toward Earth with enough accuracy. Attitude control has to preserve that pointing. The spacecraft's computer has to package information in a form the receivers can understand. Enough power has to remain for the radio system and the critical subsystems that support it. On Earth's side, the Deep Space Network has to do the listening. Goldstone, Madrid, and Canberra are placed around the planet, so the rotation of Earth does not make one long silence every day. When one complex turns away, another can take over the relationship. That geography turns a spinning planet into a coordinated listening instrument. But do not imagine ordinary listening. Voyager's signal is not like a radio station fading on a road trip. By the time it reaches Earth, it is spread thin across an enormous sphere of space. The antennas have to gather it. Receivers have to pull it from noise. Engineers have to interpret what remains. A sentence like "Earth hears Voyager" hides a great deal of work, and then there is light time. The 2025 language from NASA and JPL puts the one-way travel time for a signal at more than 23 hours. That's not just an impressive number. It changes operations. A command sent now belongs to tomorrow's spacecraft. An answer sent by Voyager belongs to another tomorrow on Earth. Every diagnostic loop is stretched until patience becomes part of the hardware. Now imagine a fault. The spacecraft behaves unexpectedly. A data field looks wrong. A mode change does not match what the team hoped to see. On a nearby spacecraft, the team might send a quick test and watch the result. With Voyager, even a simple exchange consumes days. The team has to think slowly, model carefully, and avoid making an old problem worse. So that is why the communication limit cannot be reduced to distance alone. Distance weakens the link, but a final silence could come through several doors. A transmitter could fail. Power could be insufficient. Pointing could drift. A command could no longer be executed. The Deep Space Network might hear a tone, but not enough useful information. The relationship can thin before it breaks. Here's also why the video must resist last signal melodrama. A last signal, if one is ever identified cleanly, would be emotionally powerful. But it would not mean Voyager hit the end of its path. It would mean the shared path ended. Earth would no longer be traveling with the spacecraft in a communicative sense. There's a beautiful asymmetry here. Earth can keep changing. We can maintain antennas, improve processing, coordinate arrays, and refine ways to extract faint signals. Voyager cannot upgrade itself. It can only preserve what it has left. One end of the link adapts, the other end endures, so the radio rung gives a different answer from the power rung. Voyager can travel as a communicating spacecraft only as long as both ends of the chain remain viable. That might outlast useful science in some form, or it might fail with an engineering problem before all theoretical power is spent. The key is that communication is a relationship, not a destination. When that relationship ends, Voyager becomes silent to us. But silence is not physical stopping. It becomes the end of a conversation crossing almost a light day of dark. The object continues outward, while the evidence for its next phase shifts from live telemetry to prediction records. and models. The link is also shaped by trust. A command sent to Voyager has to be built from knowledge of a spacecraft that is already far outside normal engineering experience. The team cannot see it. They cannot test the exact conditions around it. They can only use telemetry, models, old procedures, and ground-based simulations. Then they have to decide what instruction is safe enough to send. That makes each contact more than a technical exchange. It becomes a confirmation that the spacecraft still exists in the shared human system. A faint carrier proves the antenna is still oriented well enough. A packet of data proves the spacecraft can still organize a reply. Housekeeping telemetry proves the old machine still has an internal story we can read, but the relationship can degrade by degrees. Maybe the data rate has to be reduced. Maybe contacts become more selective. Maybe less science can be returned because engineering data takes priority. A speaking spacecraft can become quieter before it becomes silent. That's another reason a single final date would be misleading. Earthside listening is not free of limits. The Deep Space Network is extraordinary, but it is also a real infrastructure with schedules, maintenance, upgrades, weather, and multiple missions asking for time. Voyager's future depends partly on whether humans keep choosing to allocate attention to a very old spacecraft with very faint returns. That attention is part of the answer. If the spacecraft speaks but no one listens with enough sensitivity, the practical relationship fails. If Earth listens but the spacecraft cannot hold the beam, the relationship fails from the other side. Communication is a bridge, and a bridge has two ends. Now separate power from being heard. A powered spacecraft is not automatically a communicating spacecraft. Voyager can have a working transmitter and still need a whole chain of things to go right before Earth receives useful information. That chain is one of the most beautiful parts of the mission because it is shared across the solar system. On one end is the small spacecraft. It has to keep enough electrical power for its radio system. It has to point its high-gain antenna toward the only planet listening for it. It has to keep attitude control stable enough that the beam does not drift away. It has to encode data correctly with old electronics and old memory. Any weakness on that end matters. On the other end is Earth. Not Earth as a casual listener, but Earth as a coordinated receiving machine. Goldstone, Madrid, and Canberra give the Deep Space Network a planetary rhythm. As Earth turns, listening can pass from one site to another. The system makes our rotating planet behave, for a while, like one patient ear, but patience does not make the signal strong. By the time Voyager's transmission reaches us, it is faint beyond ordinary experience. It has spread across more than 15 billion miles in dated NASA and JPL language. It has crossed space for more than 23 hours one way. It arrives carrying less power at the receiver than a human mind can comfortably picture. Engineers do not merely hear Voyager, they extract it. That extraction depends on antennas, receivers, scheduling, calibration, software, and interpretation. The Deep Space Network also has other spacecraft to support. It has maintenance needs, it has weather and geometry, and competing priorities. Voyager is legendary, but legend does not remove logistics. Now add the delay. A problem appears in telemetry, or a strange behavior suggests the spacecraft is not doing what was expected. The team builds a command. The command leaves Earth. It spends nearly a day crossing the distance. If the spacecraft receives it, understands it, and answers, the answer spends nearly another day coming back. A simple question can require a human week. A recovery can become a slow dialogue with a machine that cannot be touched. Here's why communication is not a range number alone. The distance matters, of course. Every added mile weakens the link budget. But the final silence may not happen because Voyager reaches a clean radio boundary. It may happen because power falls too low, pointing becomes too hard, a transmitter component fails, or Earth can no longer pull a reliable signal out of the noise. The radio limit could be technical before it is poetic, and we need that discipline because last signal drama is tempting. A final carrier tone, a last packet, a date that headlines can circle. The real science is subtler. A spacecraft can become silent for reasons that do not mark a physical destination. Silence would mean the relationship has failed, not that the object has stopped moving. So under the radio link definition, Voyager travels as far as the communication chain survives. That chain includes the spacecraft and Earth together. It isn't just a property inside Voyager. It becomes a partnership stretched across interstellar distance, and there is something moving in that partnership. The spacecraft side can only age. It cannot build itself a larger antenna. It cannot install a new transmitter. It cannot replace weakened parts. Earth, by contrast, can improve methods, coordinate arrays, refine signal processing, and keep assigning attention. So the link home is asymmetrical. One side adapts, the other endures. That asymmetry gives us a clean answer. As a speaking spacecraft, Voyager 1 can travel only until its radio relationship with Earth can no longer be maintained. After that, the journey does not become false, it becomes unreported by the object itself. We can calculate the path. We can remember the last known state. We can model what happens next. But the conversation has ended. We have established the near limits first. Power narrows the living mission, and communication turns distance into a fragile relationship between an old spacecraft and Earth. What remains open is the larger boundary question. If Voyager keeps moving after those active links weaken, what has it already crossed, and what has it not crossed yet? Now we come to the boundary Voyager has already crossed, and we have to give it full weight without letting it answer too much. The heliopause is the outer edge of the heliosphere, the great bubble made by the sun's wind and magnetic influence. The sun constantly sends charged particles outward. They stream past planets, moons, dust, and spacecraft, carrying part of the sun's environment with them, far enough away that outward pressure gives way to the surrounding interstellar medium. That transition is the heliopause. It isn't a painted line, it isn't a wall, it becomes a change in plasma conditions, magnetic environment, and particle behavior. A spacecraft crossing it does not hear a gate close. It measures a different kind of space. Voyager 1 crossed that boundary in August 2012. That fact deserves to stay astonishing. For the first time, a human-made object was outside the sun's wind bubble and taking measurements from interstellar space. This was not only a symbolic achievement, it gave scientists direct evidence from a region that had previously been modeled from the inside. But here is the correction. Interstellar space, in this NASA usage, means outside the heliosphere. It does not automatically mean beyond every object or influence associated with the sun. Those are different claims. The heliosphere is about solar wind and plasma. The larger solar system boundary can be about distant comet populations and the sun's extended gravitational neighborhood. So if someone asks, has Voyager 1 entered interstellar space? The answer is yes. If someone asks, has it cleared every broad definition of the solar system? The answer is not that simple. The same spacecraft can be beyond the heliopause and still not beyond the Oort Cloud definition of the sun's outer architecture. Here's not a contradiction to hide. It's one of the clearest payoffs of the whole video. Nature gives us layered boundaries. Our language often wants one border. Voyager forces the layers apart. Think of how many edges Earth has. The shoreline is one kind of edge. The atmosphere has another set of thinning layers. A magnetic field reaches farther. A gravitational relationship reaches farther still. None of those borders is fake just because another exists beyond it. They answer different questions. The sun works the same way, but on a scale that makes the word edge feel unstable. The planets occupy one familiar region. The Kuiper belt and scattered small bodies extend the map. The heliosphere defines the wind bubble. The Oort Cloud, if counted, pushes the solar system's outermost comet reservoir into deep time. So Voyager's 2012 crossing answers one version of the title with confidence. How far can Voyager travel before it leaves the heliosphere? It already has. How far before it leaves the Sun's broader possible domain? That answer still lies far ahead, and it depends on how we define the boundary. And the science becomes more interesting because we do not flatten it. If we pretend the heliopause is everything, we lose the Oort Cloud problem. If we minimize the heliopause, we lose the first direct interstellar measurement by a human-made object. The honest treatment gives both truths their place, so the heliopause rung tells us this. Voyager 1 has already traveled beyond the Sun's wind bubble into interstellar space. That's a real boundary and a real achievement. It isn't the last boundary in every useful sense. The next rung is slower, larger, and harder to see. The word interstellar also needs care because it can sound like a genre label. We hear it and imagine starships, destinations, and dramatic crossings between suns. In Voyager's case, the meaning is more precise and more grounded. Interstellar space is the local environment outside the heliosphere, where the solar wind no longer dominates in the same way. That precision makes the achievement better, not smaller. Voyager did not become important because it suddenly belonged to science fiction. It became important because it carried instruments across a boundary that scientists had modeled, debated, and wanted to measure from the outside. It turned a theoretical edge into direct spacecraft data. The crossing also reminds us that boundaries in space are often detected by changes, not by surfaces. Particle counts change, magnetic field behavior changes, plasma clues change. The spacecraft does not need to hit anything for the environment to become different. The evidence is in the measurements. Here's a useful correction for the viewer because it prevents visual fantasy from taking over. The heliopause is not a glowing shell. It becomes a transition in an invisible medium. The Sun's influence is not a solid dome. It becomes a changing physical condition. Voyager's importance is that it could report from that transition while it was still alive enough to measure. So this boundary is not only a location in space, it becomes a before and after in what Voyager could tell us. Before it, the spacecraft was approaching the edge of the Sun's bubble. After it, it was sampling the local interstellar environment. The same object made the comparison possible. Now we reach the boundary Voyager has already crossed. The heliopause sounds like a science fiction threshold, but its importance is not imaginary. The Sun does not end at the visible edge of daylight. It sends out a flow of charged particles called the solar wind, and that wind inflates a huge bubble through the surrounding interstellar material. Inside that bubble, the Sun's outflow shapes the environment. Farther out, the surrounding medium pushes back. Voyager 1 crossed the heliopause in August 2012. That sentence should still feel astonishing. A machine built on Earth moved beyond the dominant flow of particles from the Sun and began sampling a different plasma environment. It did not leave a painted border. It crossed a physical transition identified through measurements. And yet the same sentence can mislead if we let it become too simple. Interstellar space does not mean Voyager is now cruising toward a nearby star in the way a ship heads toward a port. It means Voyager is outside the heliosphere. It's beyond the Sun's wind bubble. That's a real scientific status. Also, not the same thing as clearing every possible boundary associated with the Sun. Here's one of the central corrections in the whole answer. The heliopause answer is true and incomplete. True, because Voyager is in interstellar space by the heliosphere definition. Incomplete, because the solar system can be described by more than the reach of the solar wind. The Sun's gravitational family may extend far beyond the heliopause if we include the distant comet reservoir we call the Oort Cloud, so we should not flatten the story in either direction. We should not pretend the heliopause is the final edge of everything. We should also not treat it as a minor public milestone. It was not a ceremonial line. The spacecraft entered a region where particle and plasma conditions changed. It gave humanity its first direct measurements from that environment. Think about what that means for the title. If the question is, how far can Voyager travel before it becomes interstellar, then the answer has already happened. The spacecraft crossed that boundary years ago. If the question is, how far before it leaves the Sun's broader domain entirely, then the heliopause is only one rung on the ladder. That dual answer is not evasive. It becomes the science. Nature does not owe us a single edge just because a diagram would be easier to draw. A magnetic bubble, a planetary system, a comet cloud, and a gravitational neighborhood can all describe different relationships to the same star, and Voyager makes that visible. Before Voyager, the heliopause was a boundary inferred and modeled from inside. After Voyager, it became a boundary touched by a machine. That does not end the debate about the solar system's larger edge. It gives us one firm step before the much larger uncertainty begins. The emotional shift is important too. The heliopause is where Voyager stops being only the farthest spacecraft and becomes a probe of the space between stars. Not a starship, not an arrival machine, a measuring instrument in an environment no previous operating spacecraft had sampled from that side. So the heliopause rung answers one version of the title with confidence. Voyager 1 has already traveled far enough to leave the heliosphere. It has not completed every possible departure from the solar system. The next question is larger, slower, and much less visible. Now the word edge starts to misbehave. Most of us learned the solar system from a diagram that had to fit on a page. The sun sat in the center, the planets lined up around it. Maybe a belt of icy objects appeared near the outside. Maybe a comet had a long oval path. The picture helped us begin, but it also trained us to expect a border. Real space does not supply that border cleanly. Populations thin out, influences overlap. Boundaries depend on what we are measuring. If we measure sunlight, one answer appears. If we measure solar wind, another answer appears. If we measure where distant icy bodies may still be connected to the sun, the answer becomes far larger. So the question, has Voyager left the solar system, cannot be answered honestly until we define solar system. If we mean the region of the major planets, Voyager is long gone. If we mean the heliosphere, Voyager 1 crossed out in 2012. If we mean the distant comet reservoir associated with the Sun, then the answer is still ahead. That might feel frustrating, but it is not a dodge. It's precision. Everyday language says the solar system as if it were one object with one rim. Science uses several maps because the Sun has several kinds of relationships with its surroundings. The Oort Cloud is the most important map for this rung. NASA describes it as a theorized, distant region of icy bodies. It may form a vast spherical shell or thick bubble around the Sun, planets, and Kuiper belt. Its inner edge may begin thousands of astronomical units away, and its outer edge may extend tens of thousands or even 100,000 astronomical units from the Sun. Notice the language. Theorized, distant, may, estimates. Here's not a hard shell photographed from outside. The Oort Cloud is inferred largely from the behavior of long-period comets. We understand it because comets return from huge distances on strange orbits, pointing back to a reservoir we have not visited. That uncertainty does not make it useless, it makes it honest. The Oort Cloud is exactly the kind of boundary that exposes why one neat answer fails. A spacecraft can be beyond the Sun's wind, but still far from clearing the Sun's possible cometary family. Picture home not as a fence, but as a set of fading relationships. Near the planets, home is obvious. Beyond Neptune, home becomes a smaller sun and a colder map. Beyond the heliopause, home no longer dominates the plasma environment. In the Oort Cloud frame, home may still describe a distant gravitational association with icy bodies that remember the Sun. Voyager keeps moving through those meanings whether we name them well or not. It does not change speed because a boundary definition changes. The definitions change what answer we give to the title. So under the broad solar system edge definition, Voyager has not finished leaving in one clean sense. It has completed one departure and begun another. The heliopause was a real crossing. The Oort Cloud is a much slower departure through a diffuse, inferred region. Here's why the viewer should not feel cheated by layered answers. A one-sentence claim would be less satisfying here. It would either erase the heliopause or erase the Oort Cloud. The latter keeps both. It lets us say exactly what Voyager has done and exactly what remains unresolved. Under this boundary rung, Voyager's travel is not measured by mission operations anymore. It's measured against meanings of home. And home, at the outer edge of the solar system, is not a wall. It becomes a fading set of solar relationships stretched across deep space. Here's also where diagrams can betray us. A diagram has to simplify. It draws the heliosphere as a bubble, the Kuiper belt as a band, and the Oort Cloud as a shell. Those shapes are useful, but they can make the outer solar system look more solid and tidy than it is. Voyager's path cuts through the limitations of the picture. The spacecraft does not experience a labeled sequence of textbook zones. It experiences local conditions. It's in a place where the sun is still the source of its origin story, where the heliosphere is behind it, and where the next broad boundary is something humans infer from comet behavior rather than something a spacecraft has mapped. That makes the phrase "leaving the solar system" depend on the question being asked. Are we asking about plasma? Then the heliopause matters most. Are we asking about planets? Then Voyager is far beyond the familiar architecture. Are we asking about objects loosely bound to the sun and supplied from a distant reservoir? Then the answer moves outward by enormous factors. The useful thing is not to choose one definition and pretend the others are wrong. The useful thing is to state which definition is being used. That's how the viewer gets a satisfying answer instead of a fight over words. The fight over words usually happens when the map is too small. If the map includes only planets, Voyager looks completely outside. If the map includes the sun's wind, it is outside in another sense. If the map includes the Oort Cloud, the story stretches again. Bigger maps create calmer answers. They also keep Voyager from becoming a slogan. The spacecraft is not proof that one boundary solves all boundary questions. It's proof that a real object can move through several scientifically useful edges, each one changing the answer in a different way. Now the edge gets messy in the best scientific way. Most of us first learn the solar system as a clean picture. A sun, a row of planets, maybe an asteroid belt, maybe a few dwarf planets and comets at the edge. That picture is useful for beginning, but it gives the wrong emotional impression. It makes the solar system feel like a room with walls. Space does not arrange itself for classroom diagrams. The outer solar system thins, populations overlap, influences fade instead of stopping cleanly. The sun can dominate one kind of environment while another kind of relationship extends much farther. So when someone asks whether Voyager has left the solar system, the honest answer has to ask what boundary they mean. If they mean the heliosphere, Voyager 1 is outside it. If they mean the region of familiar planets, it passed that scale long ago. If they mean the possible distant reservoir of comets still linked to the sun, then Voyager has not cleared the story at all. That distinction is not wordplay. It changes the answer by tens of thousands of years. The solar system has several edges because edge is not one property. There's an edge to the sun's wind. We can see edges to known small body populations. There's the limit of practical spacecraft operations. There's the inferred reach of long-period comet sources. Each boundary answers a different question. Here's where Voyager becomes more valuable as a teaching object than as a trivia fact. A trivia fact wants one sentence. Voyager left the solar system, or Voyager did not. The real answer says yes under one definition and not yet under another. That might sound less clean, but it is more satisfying because it explains why intelligent sources can sound different without necessarily contradicting each other. Picture a coastline. The beach is one boundary, territorial waters are another. Weather systems, trade routes, and ecological zones all draw different maps around the same place. No one boundary cancels the others. It depends on what relationship we are measuring. The solar system is stranger and larger, but the logic is similar. Now bring Voyager back into the frame. The spacecraft is not waiting for humans to settle a vocabulary debate. It keeps moving. Our definitions ride along behind it, trying to describe what kind of place it is in. When the sun's wind no longer dominates, one label changes. When the distant Comet Cloud is eventually approached, another label becomes relevant. When nearby stars become better reference points than the sun, another kind of map takes over. So that is why the ladder matters. Without the ladder, the viewer gets trapped between two oversimplified answers. With the ladder, every answer has a place. Heliopause, crossed. Broad cometary boundary, not yet. Star proximity, later and still not arrival. Galactic motion, ongoing. This boundary rung also keeps the tone honest. We do not need to make Voyager more dramatic by pretending it passed every possible edge in 2012. The real drama is that the first confirmed interstellar boundary was only the beginning of a much longer departure. That's more humbling than a clean finish. So under the solar system boundary definition, Voyager's travel is governed by whichever edge we choose to count. The heliosphere gives one completed answer. The Oort Cloud gives a future measured in centuries and millennia. The spacecraft itself does not care which definition wins. It keeps going while the meaning of home stretches behind it. Now let the Oort Cloud set the scale. Voyager 1 moves so fast that ordinary comparisons break almost immediately. Roughly 17 kilometers per second relative to the Sun, about 1 million miles per day in NASA's public Oort Cloud framing. A number like that feels final, because human travel has no experience with it. Then the Oort Cloud makes the number feel small. NASA's scale estimate says Voyager 1 will not enter the Oort Cloud for about 300 years. It may take around 30,000 years to pass beyond the outer edge. That's the kind of contrast this video was built for. A spacecraft can move 1 million miles a day and still needs centuries just to approach the next broad boundary. But we need to picture the boundary correctly. Do not imagine a snowy shell waiting in the dark like a wall. Do not imagine a mission event with a countdown clock and a clean crossing report. The Oort Cloud is diffuse. Its inner and outer reaches are estimated. Its bodies are sparse. Its existence is inferred from comet behavior, not from a camera drifting through a visible cloud. So what does it mean to enter it? It means Voyager's path would reach the scale where that distant reservoir is thought to begin. What does it mean to pass beyond it? It means moving outside the estimated outer reaches of that reservoir. If those estimates hold, these become not sharp threshold events. They are scale answers, and those scale answers are still powerful. 300 years is long enough to detach the object from every practical plan of the current mission. 30,000 years is longer than recorded civilization. If Voyager is still intact then, it will almost certainly not be a spacecraft in the living sense. It will be an artifact whose path is known because of calculations and records, not because it is chatting with Earth. That changes how we should hear the word travel. For the Oort Cloud rung, travel no longer means control. It does not mean useful telemetry. It does not mean a mission team waiting for a flyby. It means the physical object carrying a human-made shape through an estimated outer architecture of the Sun. There's a strange intimacy in that. The Oort Cloud is incredibly remote, yet it still belongs to the idea of the Sun's home territory. Long-period comets may come from there. The Sun's gravity is part of why we discuss it as our outermost region. Voyager, by then, would be almost absurdly far from the warmth and brightness we associate with home, and still possibly inside a boundary named for the solar system. So that is why the heliopause crossing and the Oort Cloud timing must sit together. The first tells us Voyager is in interstellar space by the solar wind definition. The second tells us the broader question of leaving the Sun's outer domain may take tens of thousands of years. Now think of the emotional scale. The spacecraft's powered life is measured in years and engineering decisions. The Oort Cloud answer is measured in centuries and millennia. The same object connects those clocks. A heater choice now belongs to one clock. A Comet Cloud estimate belongs to another. The title question needs both, because Voyager is both an aging machine and a mass on a trajectory. We also have to protect the uncertainty. Maybe the Oort Cloud's exact shape is different from our best public description. Maybe its outer edge is not where a simple number places it. That does not destroy the answer. It tells us the answer is approximate because the boundary itself is approximate. So under the Oort Cloud definition, Voyager can travel for centuries before entering the Sun's distant comet reservoir, and perhaps about 30 millennia before moving beyond its outer estimated reach. By that time, the mission will almost certainly be history. The motion will not. Now we enter the scale where Voyager's speed stops feeling fast. Voyager 1 is moving at roughly 17 kilometers per second relative to the Sun. In human terms, that is almost absurd. It covers about 1 million miles per day. No road, aircraft or ordinary travel comparison survives contact with that number for long. Then the Oort Cloud makes it feel small. The Oort Cloud is not a wall of comets waiting in a neat shell. It becomes an inferred, diffused reservoir, understood largely through the orbits of long-period comets that seem to come from vast distances. Its boundaries are estimates, not fences. Its population thins into the surrounding galactic environment. That makes it hard to picture, and that difficulty is part of the lesson. NASA's public Voyager framing gives the useful scale. Voyager 1 will not enter the Oort Cloud for about 300 years, and it may take around 30,000 years to pass beyond it. Those numbers should slow the narration down. 300 years is already beyond every practical mission plan. 30,000 years belongs to deep history, and the spacecraft is not waiting for a signpost. No camera will wake up and show a cloud wall. No sensor suite is expected to celebrate an arrival in the ordinary mission sense. By then, if the present expectations hold, Voyager will be silent as a normal operating spacecraft. It will be a calculated object, not a speaking participant. That changes the emotional meaning of distance. A human mission can plan an encounter. A silent artifact can only pass through a future we model from its trajectory. The 300-year number is not a calendar appointment for engineers. It becomes a physical estimate for where an object will be long after the working relationship may be gone. The Oort Cloud also protects us from a common mistake. Once we hear that Voyager is in interstellar space, we may imagine the Sun's story has ended. But if the distant comet reservoir is part of the solar system's broad architecture, then Voyager still has an enormous solar-associated region ahead. It has left the wind bubble. It has not necessarily finished leaving the Sun's outermost family. Now notice the paradox. The Oort Cloud is tied to the Sun, but the Sun itself would be only a distant star from Voyager's perspective by then. The spacecraft would be moving through a region where home is more gravitational memory than visible dominance. That's a strange idea, still inside a possible solar boundary, yet emotionally and practically beyond anything that feels like the solar system of childhood. Here's why the Oort Cloud belongs in the center of the documentary. It turns the title question from a heroic escape story into a scale problem. Voyager can be our fastest departing artifact, and still require millennia to clear a boundary that is not even sharply drawn. And we have to keep the language careful. The Oort Cloud is inferred. Its inner and outer extents are not measured like the edge of a spacecraft tank. It's better to say Voyager may enter and may pass beyond, using NASA's approximate scale, than to pretend we know the boundary with surveyor precision. So the Oort Cloud answer is both large and conditional. If we count the broad cometary boundary as the solar system's outer reach, Voyager 1 has centuries before it even enters that region and perhaps about 30 millennia before it is beyond it. That's not the end of motion. It's only the end of one very expanded meaning of home. Now compare the 300-year estimate with the Living mission. 3 centuries is far beyond the expected life of the active spacecraft. Also, short compared with the 30,000-year outer estimate. The Oort Cloud gives us a staircase inside the staircase. First approach, then long passage, then possible departure from the broad reservoir. That layered scale prevents a common misunderstanding. The Oort Cloud is not a single ring at one distance. NASA's public descriptions give broad ranges because the region itself is expected to be vast and diffuse. The inner edge may begin thousands of astronomical units from the Sun. The outer edge may lie tens of thousands to 100,000 astronomical units away. A spacecraft can be associated with that region for an enormous span without any dramatic event marking the change. This matters for the title because it shows how a simple distance question becomes a boundary problem. If we only ask where Voyager is today, we miss the future architecture. If we only say it is in interstellar space, we miss the Sun's possible distant comet reservoir. If we only say it has not left the solar system, we erase the heliopause crossing. The right answer holds the tension. Voyager is beyond the Sun's wind and still may have a long way to travel before it is beyond the widest common solar system frame. That's not contradiction, that's scale, and scale is exactly what the title needs. The viewer did not click for a vocabulary trick. They clicked because one familiar spacecraft makes impossible distances feel personal. The Oort Cloud keeps that promise by turning a known machine into a ruler for a region we cannot yet directly see. We have now separated the Sun's wind from the Sun's wider possible domain. Voyager is already beyond the heliopause, while the Oort Cloud scale stretches the departure into centuries and millennia. What remains open is the star question. Does all that future distance mean Voyager is going somewhere real? Now we reach the famous future milestone that needs the most careful language. Voyager 1 is often associated with AC plus 79 3888, also called Gliese 445. NASA and JPL's public description says that in about 40,000 years Voyager 1 will pass within about 1.7 light-years of that star, and at that time that star will be nearer than the Sun as a reference point. Those are the facts we need. But the way we say them matters. The event is proximity. Its closest approach. It isn't a visit, it isn't a planned port. It isn't a spacecraft slowing down into a new neighborhood. Voyager will continue on its path, and the star will be moving too. The future closeness happens because both objects are part of the moving galaxy. About 1.7 light-years can sound small only because astronomy has trained us to compare it with larger gaps. In human terms, it is enormous. Light itself needs about 1.7 years to cross that distance. Voyager's current radio delay is measured in hours. The future separation from Gliese 445 is measured in years of light travel, so if the viewer imagines the spacecraft gliding near a star the way a probe passes a planet, the image is wrong. A planetary flyby can pass close enough to bend a trajectory dramatically and return detailed measurements. The Gliese 445 event is nothing like that. It becomes a distant passing relationship on a stellar map, and that is more interesting than the false version. The false version says Voyager is headed somewhere. The true version says that even after 40,000 years, one of the most famous future milestones is still a lesson in how far apart stars are. Now listen to the phrase closer to Gliese 445 than to the Sun. It's important, but it can mislead. Closer than the Sun does not mean close. It only means the Sun has become more distant than another reference point. That's a ranking of distances, not an arrival story. This distinction protects the core promise. The video is not trying to make Voyager smaller, it's trying to make scale honest. A named future star gives the viewer something to hold on to. The correction gives the number its real meaning. It also keeps the story away from contact bait. We do not need to imagine discovery by someone else. We do not need to turn the spacecraft into a message in search of an audience. The scientific point is stronger without that. A human-made object can move for tens of thousands of years and still not meaningfully go to a star. That sentence is humbling. It tells us more about interstellar space than a louder myth would. It says the stars are so far apart that a high-speed departing spacecraft can spend 40,000 years moving and still only achieve a light-year scale proximity. Now place Gliese 445 back inside the ladder. It comes after the heliopause. It comes after the Oort Cloud scale. It belongs to a future where Voyager is probably silent, probably uncommanded, and certainly not performing a designed encounter. It becomes a reference point for the object, not a destination for the mission. So under the nearby star definition, Voyager travels far enough that another star can temporarily become a closer reference than the Sun. But that closeness remains astronomical, not human. The answer is not that Voyager goes to another star. The answer is that it passes within about 1.7 light-years of Gliese 445 in a moving stellar neighborhood. Near is doing all the work here. Near can be true and still almost unimaginable. Near can be a scientific comparison and not a travel ending. Voyager teaches that difference with one quiet future pass. The moving star detail is essential here. If Gliese 445 were a fixed target on a fixed map, the story would invite the wrong mental picture, but stars have their own velocities. The Sun has its own motion. Voyager's future proximity happens in a changing arrangement, not because the spacecraft was aimed like an arrow at a stationary mark, so that is why the catalogue names matter without becoming the drama. AC plus 79, 3888 and Gliese 445 give us a real object to discuss. They keep the future from becoming vague, but the named star is not a promised endpoint. It becomes a future reference in a galaxy where references keep changing. There's another subtle reset. 40,000 years sounds so large that a viewer may assume almost anything can happen by then. But even across that time, Voyager's speed is tiny compared with the separation between stars. The number does not prove that interstellar destinations are easy. It proves the opposite. It shows how stubbornly large the gaps remain. That makes the milestone valuable for the exact title. If someone asks whether Voyager will eventually get somewhere, the Gliese 445 event is the clean correction. It gets close only in the astronomical sense. It becomes nearer to that star than to the Sun, while still separated by about 1.7 light-years. That number should stay in the listener's ear. It's close enough for astronomers to name, and far enough to defeat ordinary travel intuition. Voyager will have crossed timescales that dwarf civilization, and the famous star comparison still leaves a gulf that light measures in years. Now we reach the future fact that is easiest to say badly. Voyager 1 is often linked with Gliese 445, also catalogued as AC plus 79 3888. Because in about 40,000 years it will pass within about 1.7 light-years of that star. The sentence is true in the broad public NASA and JPL framing, but it has to be handled with care. If we let the words become casual, the viewer hears a destination. That's not what the event is. Voyager 1 is not aiming for Gliese 445 like a spacecraft on approach. It will not slow down, it will not enter orbit, it will not cross some operational arrival zone. It will pass through a moving stellar neighborhood while the star itself is also moving. The event is a closest approach, not a meeting. About 1.7 light-years is close only by the standards of distances between stars. It's still an enormous gap. Light itself takes about 1.7 years to cross it. Compare that with the current radio delay of a little less than a day one way in the dated Voyager material, and the scale change becomes almost brutal. a distance that astronomy can call nearby, is still far beyond any mission-like encounter. Here's why the right words matter. Proximity, closest approach, passing within about 1.7 light-years. Those phrases let the milestone keep its weight without turning it into a false story, and the milestone earns its weight. 40,000 years is so far outside normal imagination that the number almost becomes abstract. Yet after that span, Voyager has still not gone to another star in the familiar sense. It has only come closer to one star than to many others. The fact does not shrink the galaxy, it enlarges it. Now think about the Sun in that future. Voyager's relationship to the Sun will be very different from the relationship it has now. The Sun will be distant. Other nearby stars may become more useful markers. Gliese 445 may be closer than the Sun at that time. But closer than the Sun is not the same as close. It becomes a ranking, not a rendezvous. That difference is one of the most important viewer resets in the video. The human brain wants a travel story to have destinations, a launch, a route, a port, a final place. Voyager's future refuses that structure. Its path has notable proximities, but not planned stations. So under the stellar proximity definition, how far can Voyager travel? Far enough that a star other than the Sun becomes a closer reference point on a galactic map. Not far enough to make that star a destination in any ordinary spacecraft sense. That answer is quieter than the myth, and much better. It also keeps the video away from alien contact bait. We do not need to imagine someone finding Voyager near Gliese 445. We do not need to pretend a message is the main scientific payoff here. The serious payoff is scale. The spacecraft teaches us how enormous stellar distances remain even after tens of thousands of years of high-speed outbound motion. The Gliese 445 event becomes a correction disguised as a milestone. It gives the audience a name, a time, and a distance, and then asks them to rethink what near means. Near is not arrival, near is not target, near is not mission success. Near is the least distant relationship in a moving galaxy at that future time. Now the star map begins to slide under our feet. Now we can place the next piece. It's natural to picture Voyager's future as a line drawn across a fixed background. The Sun behind, Gliese 445 ahead, the spacecraft moving across a dark chart. That picture is simple, and for a few explanatory beats it helps. But it is not the real long-term situation. The Sun moves around the Milky Way. Nearby stars move. Gliese 445 moves. Voyager moves. Gas, dust, stellar neighborhoods, and gravitational influences are all part of a dynamic galaxy. There's no still wall map with Voyager's route permanently printed on it. That means the title question has to carry a reference frame. How far from Earth? How far from the Sun? How far from the heliopause? How far from the estimated Oort Cloud boundary? How far from that future Gliese 445 proximity? Each frame gives a legitimate answer. None of them alone is the final answer. We hide reference frames in everyday life because the ground feels still. If you drive 10 miles, everyone knows what you mean. But Earth rotates, orbits the Sun, and travels with the Sun through the galaxy. Our local experience lets us ignore that motion. Voyager's future does not. Once the spacecraft is silent, its future becomes a model more than a report. We can use its last known state, gravity, measured stellar motions, and chosen coordinates to estimate where it will be. That modeling can be very good, but it is still modeling within moving frames, not a simple itinerary. Here's where deep time changes the emotional shape of the story. In the mission era, Voyager's location is part of an active relationship. Earth asks. Voyager answers. In the galactic era, Voyager's location becomes a predicted state in a moving system. The object remains real, but the way we know it changes. Now think about a closest approach. It isn't a place where the story ends. It becomes a point when two moving paths produce a minimum distance. After that, the relationship changes again. Another star may become more relevant. The Sun's distance keeps changing. The spacecraft's path remains continuous, but our named milestones come and go. So that is why destination language fails. Destinations are human tools. We choose them, we slow down for them, we build routes toward them. Voyager, after the mission, has no such structure. It has trajectory, velocity, and gravity. Its future is not meaningless, but it is not arranged like a trip. The moving galaxy also introduces honest uncertainty. Small measurement uncertainties matter more as time grows. Gravitational nudges can accumulate. Future stellar encounters can be estimated, but not narrated with infinite precision. A responsible answer gives the broad shape without pretending every future coordinate is known. This restraint matters for the viewer. It says we are not dodging wonder, we are refusing fake certainty. The real wonder is that a spacecraft launched for planetary science has become part of a question about reference frames, galactic motion, and what distance means when the map itself moves. So under the galactic motion definition, Voyager can keep traveling as long as the object or its remnants continue through the Milky Way's gravitational environment. Its distance from one reference may grow while its distance from another shrinks. It can pass through changing neighborhoods without any one of them becoming a final address, and that gives the title a wider but cleaner answer. Voyager's future is not a line to a destination. Its motion through a moving galaxy, described by changing relationships. A reference frame is not a technical nuisance. It becomes the thing that makes a distant statement meaningful. If we say Voyager is farther from Earth, we are using Earth. If we say it is farther from the Sun, we are using the Sun. If we say it is closer to Gliese 445 than to the Sun in the future, we are comparing two moving relationships at one future interval. Here's why deep time maps should be treated with humility. They can be useful and beautiful, but they are not fate. They show a calculation, a model, a set of assumptions, and a chosen way of measuring. The farther forward the map goes, the more the viewer should understand the difference between broad confidence and false exactness. Voyager's own motion is not mysterious in the magical sense. It follows gravity. It carries velocity. It responds to the environment around it. The mystery is conceptual. What answer should we give when the object has no planned target, when every marker moves, and when the definition of far changes with the reference point? So that is why the galactic frame does not drift away from Voyager. It brings Voyager into a larger truth. The spacecraft is no longer only a mission from Earth. It becomes a tiny mass joining the population of moving things in the Milky Way. That does not make Voyager less special. It makes the specialness more exact. To us, it carries a human origin. To gravity, it is mass and motion. The documentary lives between those truths, keeping the object emotionally recognizable while letting physics remove the easy ending. Now the map itself starts moving. It's natural to draw Voyager as a point on a line. The Sun sits behind it. A star sits ahead. The spacecraft moves from left to right through a dark background. That picture helps at first, but deep time breaks it. The Sun is not fixed. Nearby stars are not fixed. Gliese 445 is not a waiting lamp at the end of a road. Voyager is not crossing a motionless stage. Everything useful in the long-range picture is moving through the Milky Way under gravity. That means the title question has to become more precise. How far from Earth? How far from the Sun? How far from the heliopause? How far from the Oort Cloud boundary? How far from Gliese 445 at closest approach? How far along a galactic path? Each answer uses a different reference point. For a mission update, that may sound too technical. For this documentary, it is essential. Distance is always distance from something. In ordinary life, the something is obvious. In deep space, especially across thousands and millions of years, it is not. Think about Earth itself. Earth rotates. Earth orbits the Sun. The Sun orbits the center of the Milky Way. The galaxy has its own motion relative to other galaxies. We usually hide these layers because local life does not need them. Voyager forces them back into view. Once communication ends, future tracking becomes prediction and reconstruction. Astronomers can model a trajectory relative to chosen coordinates. They can update with known stellar motions, gravitational influences, and uncertainties. But there is no single cosmic map stamped onto space with Voyager's final path drawn permanently on it. A trajectory is real because it is measured in a frame, not because the frame is absolute. This may sound abstract, so bring it back to the object. Voyager 1 is a physical spacecraft. It has mass, it has velocity, it will keep responding to gravity. Its path can be calculated with the best data available. The abstraction enters when we ask what that path is far from, and this is where the moving galaxy gives the title its widest shape. Voyager can keep traveling without ever having a final destination because the landscape is not arranged as destinations. Stars pass, neighborhoods change. The Sun's relevance fades in some ways and remains in others. A future closest approach becomes a temporary relationship, not a final state. The moving frame also keeps us from overstating certainty. The farther forward we project, the more small uncertainties grow. Stellar positions, gravitational nudges, and the condition of the spacecraft all matter differently over deep time. We can say the broad story with confidence. We should be cautious about pretending to know every detail indefinitely. That caution is not weakness, it's what makes the answer trustworthy. Voyager's route is not a mythic arrow into a fixed heaven. It becomes a path through a dynamic galaxy, described by physics and limited by measurement. So under the galactic motion definition, Voyager travels as long as the object or its remnants continue on a trajectory through the Milky Way. The distance can keep increasing from some reference points while decreasing from others. The journey is real, but the phrase "how far" has to carry its reference frame with it. Now we ask what remains when the mission, the signal, and the easy milestones have all faded. A silent Voyager is easy to imagine as immortal. Space looks empty. The spacecraft is small, the distances are enormous. Nothing seems likely to hit it. That intuition is partly right and partly too clean. Interstellar space is sparse, not perfectly empty. Dust exists, radiation exists, micrometeoroid impacts remain possible. Materials age, surfaces change. Insulation, metals, adhesives, wiring, and electronics face timescales far beyond their design assumptions. Voyager was built to survive a planetary mission, then an extended mission, then an old age almost no spacecraft reaches. It was not built as a museum object designed to stay perfect for millions of years, so physical survival has to be phrased carefully. Long survival is plausible. Guaranteed intact survival is not. That sentence matters because the deep time version of the Voyager story can become too grand. We want the spacecraft to become an eternal monument. We want the object to keep its shape because the shape carries the human meaning. But physics does not protect symbols just because symbols matter to us. Voyager is not one simple thing. Picture a spacecraft bus, a high-gain antenna, booms, instruments, wiring, thermal blankets, fasteners, and surfaces facing a future no engineer can inspect by hand. Some parts may endure better than others, some may degrade while remaining attached. Some may become brittle, some may be changed by radiation. Some tiny impact could scar a surface without destroying the craft. A rarer event could do more. That raises a strange but important question. If Voyager becomes damaged but recognizable, is it still Voyager for the purpose of the title? In ordinary language, yes. If a boom separated, the answer would become harder. If the main body stayed intact, but every instrument was dead, most of us would still call it Voyager. If only fragments remained, then matter from Voyager would keep traveling, but the artifact as a coherent spacecraft would have become something else. We do not need to solve that boundary perfectly. We need to mark where certainty ends. As an intact artifact, Voyager may travel for immense spans if nothing destroys or dramatically alters it. As material, pieces of Voyager could keep moving even longer, but the farther forward we look, the less confident we can be about the exact condition of the object we are naming. And this is not a sentimental problem dressed up as science. It sits inside the question. The title asks about Voyager 1, not merely atoms that were once arranged as Voyager 1. Distance alone cannot answer that. We also need condition. Is the traveler intact? Is it recognizable? Is it still one object, or has deep time converted the journey into several related paths? Think of an old shipwreck. If the hull is mostly present, we still call it the ship. If the planks scatter across the seabed, we speak differently. The identity thins as the structure thins. Space is not an ocean, but the logic helps. An artifact is not only material. Recognizable arrangement turns matter into the thing we name. Voyager's deep future lives in that tension. To gravity, it is mass and motion. To us, it is a made thing with a history. The farther it goes, the more those two descriptions can pull apart. Sparse space makes catastrophic encounters unlikely on human timescales. That is the first source of calm. Voyager is not plowing through a crowded storm of rocks. Around it, emptiness is the dominant condition. But unlikely is not the same as impossible forever. Deep time changes the meaning of risk. A tiny probability repeated across enormous spans becomes harder to dismiss with ordinary intuition. Radiation is quieter. Dust is quieter. Thermal cycling is quieter. Surface changes are quieter. None of them gives the story a clean, dramatic ending. They make the future less certain by slow pressure rather than by spectacle. So the survival rung should stay modest. We can say the motion continues. We can say long survival is plausible. We can say exact condition becomes uncertain. Those three statements are enough. They keep the wonder intact without turning uncertainty into mythology. They also keep the answer connected to the earlier rungs. Power asks whether the spacecraft can stay useful. Communication asks whether Earth can still hear it. The heliopause asks what environment surrounds it. The Oort Cloud asks which solar boundary we are counting. Gliese 445 asks whether future proximity is arrival. Survival asks whether the object itself remains the object we mean. Each rung removes a kind of certainty. That pattern matters. The mission can end while the object continues. The signal can end while the path continues. A boundary can be crossed while another remains ahead. A star can become closer without becoming a destination. And an artifact can keep moving while its exact condition becomes harder to know. So under the physical survival definition, Voyager can travel far beyond any human mission time, perhaps for immense spans as an artifact or as material, but the claim has to carry its limit. We should not say it travels forever as Voyager 1 in the intact, recognizable sense. We should say the object may persist for a very long time, and the material may persist longer still, while certainty about its state fades, and enough wonder remains in that restraint. A bolt, a dish, a boom, and a bus made by human hands can continue through space long after the people who built them are gone. The object can outlast its last command. It can outlast its last signal. It can outlast every practical mission document that once gave it instructions. But wonder does not require a promise of immortality. The honest claim is smaller and stronger. Voyager may keep traveling long after it stops being useful, and perhaps long after anyone could verify its condition directly. Now the final rung is in place before the ladder comes together. We have followed the spacecraft from active mission to signal, from signal to boundary, from boundary to deep time proximity, and from proximity to the condition of the artifact itself. The next move is not to add another topic. Now the original question can be answered with all the definitions separated. Or, here's another reason to keep this run grounded. Voyager carries cultural meaning, but cultural meaning does not change the physics of survival. The golden record matters because it makes the spacecraft more than hardware in our imagination. It carries sounds, images, greetings, and a human hope that something might understand the origin of the object. But for the distance question, that record is part of the artifact, not the engine of the answer. If the record survives, it survives as material on the spacecraft. If its surface changes, the symbolic meaning remains in our records even if the physical object becomes less readable. That difference matters. The message we assign to Voyager may last in archives, stories, and science education. The physical record has to face space, so we should not turn the artifact rung into an alien contact story. Contact would be a different question. It would require another chain of assumptions: who finds it, when, under what conditions, and whether it can be understood. The approved question here is quieter and stronger. What happens to the object itself when no one can talk to it? The best answer is almost austere. It keeps moving. It may stay intact. It may not. It remains connected to us by origin, not by communication. The further it goes, the more its human meaning depends on memory and records back here, while its physical future depends on a sparse but real environment out there. That split is powerful because it mirrors the whole video. At every stage, one relationship falls away while another remains. Instruments fail, but engineering may remain. Engineering ends, but radio may remain. Radio ends, but trajectory remains. Coherent artifact may fade, but material remains. Voyager's journey is not one thing stopping. Relationship by relationship, the connection thins, and that is why the survival run cannot be skipped. Without it, the answer would stop at the last good map point. With it, the listener understands what the very last definition of travel costs. It costs certainty about the traveler itself. Now the ladder can finally answer without pretending to be one number. The opening question sounded simple because the word travel was doing too much work. We have separated it. Now every rung has its own limit, its own distance scale, and its own kind of ending. As a living spacecraft, Voyager 1 is bounded by power, warmth, commandability, attitude control, and surviving systems. That is the closest answer. Engineers still make choices for an old machine. The measurement is remaining margin, not the next star. As a science platform, the answer is narrower. Voyager can only travel as a science-returning probe, while instruments that matter remain alive and useful. The spacecraft may keep operating after that, but the meaning changes. It may still be a machine. It may still answer. But the rich scientific return has already been reduced and will narrow further. As a communicating spacecraft, Voyager depends on a relationship across space. Its transmitter has to work. Its antenna has to stay pointed. Its power and computers have to cooperate. The deep space network has to hear a signal that grows fainter with distance. A radio answer can end without the body of the spacecraft stopping, and this may be the most important correction in the entire video. Silence is not stopping. If Voyager stops speaking, the object does not vanish. It becomes unavailable. It becomes something we know through its last state, its trajectory, and our models. The conversation ends before the motion does. As a heliopause crosser, Voyager 1 has already answered one version of the title. It has traveled beyond the sun's wind bubble. The August 2012 crossing matters because it was a real physical transition, measured by a human-made object. It should not be minimized, but that is not every boundary. If the question is about the broadest common solar system frame, the Oort Cloud keeps the answer open. NASA's public scale gives about 300 years before Voyager reaches the Oort Cloud region. and perhaps about 30,000 years before it passes beyond the estimated outer edge. Those numbers are approximate because the boundary is diffuse. They are still essential because they show how much larger the outer solar story is than the heliopause alone. As a nearby star passerby, Voyager gives us the cleanest correction to destination thinking. In about 40,000 years, it passes within about 1.7 light-years of AC plus 79 3888, also called Gliese 445, and that star may be nearer than the Sun as a reference point. That is proximity, not arrival. A stellar-scale relationship is not a port. As a galactic artifact, Voyager has no clean final station. The Sun moves. Other stars move, Voyager moves. A future path can be modeled, but not turned into a simple route with an endpoint printed at the end. Distance has to be distance from something, and in deep time the something keeps changing. As physical material, Voyager may persist for immense spans, but its exact condition becomes less certain the farther forward we look. It may remain recognizable, it may degrade, it may become pieces. The motion can outlast the identity we attach to the intact spacecraft. So the answer is not vague. The answer has layers. The mission ends first. The richest science narrows. The signal eventually fades. The heliopause is already behind it. The Oort Cloud scale stretches ahead for millennia. The Gliese 445 proximity waits in deep future without becoming a visit. Beyond that, the spacecraft belongs to galactic motion and physical uncertainty. So a daily tracker number cannot carry the whole answer. Today's distance changes, the structure remains. Power, communication, heliopause, Oort Cloud, stellar proximity, galactic motion, and physical survival are different answers to the same title. Now say the title again in plain terms. How far can the Voyager 1 travel? As a mission, only as far as the last useful systems allow. As a signal, only as far as the link home survives. As an object, far beyond silence. Through the Sun's outer boundary regions over thousands of years, near a moving star without visiting it. And onward through a galaxy where no single destination owns the path. And the answer stays clean because it refuses to cheat. A single number would have to choose one rung and hide the rest. It could be a present distance from Earth. It could be a remaining mission estimate. It could be the heliopause crossing. It could be the Oort Cloud timescale. It could be the Gliese 445 distance. It could be a deep time model. But one number cannot honestly be all of those at once. The ladder lets every answer keep its proper size. And Voyager 1 remains useful for science storytelling for the same reason. It refuses every oversimplified version. Voyager is not merely dying soon because the object will keep moving, nor is it going to a star because the famous future event is still separated by light years. One boundary does not mean every frame has been left behind, and immortality in the easy sense fails too, because the artifact itself faces deep time uncertainty. The spacecraft teaches by forcing distinctions. Motion is not mission. Proximity is not arrival. Silence is not disappearance. A boundary is not necessarily the final edge. Survival is not guaranteed identity forever. Once those distinctions are clear, the question becomes calmer. We do not need a louder ending. We do not need a myth. The real scale is already enough. Voyager 1 can lose almost every familiar sign of a spacecraft mission and still remain a traveler. The title was hiding that answer in plain sight. But there is one more reason the ladder matters. It gives the viewer closure without pretending the universe supplies one. Voyager has limits as a mission, limits as a signal, and uncertain endurance as material. Yet the motion carries past those human endings into a wider future that does not look like a route with a finish line. That language is not weaker than a single number. The phrasing is more faithful to the object. Voyager 1 keeps turning simple distance into a series of physical tests, and each test tells us where one meaning of travel ends before the next one begins. Gliese has another way to hear the ladder. Each rung changes the verb. The living spacecraft operates. The science platform measures. The communicating spacecraft answers. The silent object drifts. The heliopause crosser records a boundary already passed. The Oort Cloud traveler moves through an estimated outer scale. The stellar passerby approaches without arriving. The galactic artifact continues without a destination. Those verbs matter because they keep us from smuggling one meaning into another. If we say Voyager travels, we should ask which verb is hiding underneath. Does it operate? Does it measure? Does it answer? Does it merely move? Each answer is honest only if the verb is honest. This also explains why the title remains emotionally satisfying after the definitions multiply. Definitions often feel like they make a question colder. Here they make it warmer because they preserve the human part instead of flattening it. The living mission is not swallowed by deep time. It gets its own rung. The faint signal is not treated as trivial just because the object will continue. It gets its own rung. The future artifact is not treated as magic. It gets its own rung. So the ladder does not drain the wonder. It protects it. It lets the near-term engineering feel precious. It lets the heliopause crossing feel real. It lets the Oort Cloud scale feel enormous. It lets Gliese 445 feel humbling instead of misleading. It lets the deep time artifact feel uncertain without feeling empty. Now bring the whole structure back to the viewer's first instinct. The instinct was probably to ask, how far until Voyager stops? But the more accurate question is, which kind of stopping do we mean? Stopped operating, stopped measuring, stopped answering, stopped being within one boundary, stopped being recognizably intact. Those are different endings, and some of them may arrive while others remain far away, so the answer can be calm. It does not have to pretend we know more than we know. It can state the firm pieces, mark the uncertain pieces, and still leave the viewer with a complete shape. The firm pieces are strong. Voyager 1 exists. The spacecraft is outbound. The heliopause is behind it. Its power is declining. Its signal depends on a fragile chain. The Oort Cloud timescale is enormous. The Gliese 445 event is proximity. Deep time makes condition uncertain. The uncertain pieces are honest. How long the last active systems last. How long the radio chain remains useful. Exactly where the diffuse outer boundary should be placed. Exactly what condition the spacecraft will be in after immense spans. Exactly which future reference frame will feel most meaningful. Put together, those facts and uncertainties give a better answer than any one number could. One final protection is needed before the close. The ladder is not a way of avoiding the title. The ladder makes the title precise. If a viewer wanted the shortest possible version, it would be this. Voyager's active mission is limited by aging hardware, its signal is limited by a fragile radio relationship, and its physical motion can continue far beyond both. But the short version loses the texture that makes the answer satisfying. It does not show why the heliopause matters. It does not show why the Oort Cloud complicates the phrase solar system. It does not show why a named star can be a near pass and still not be a destination. The full answer matters because each misconception is tempting. One version says Voyager has already left the solar system and stops there. Another says it will reach another star and lets the sentence sound like a rival. Another says it will travel forever and ignores the condition of the object. Another says the mission will end soon and treats that as the end of the journey. Each tempting answer is partly true in one frame and misleading in another, so the best response is not louder. The cleaner answer wins. Voyager has already crossed a real boundary, but not every broad solar boundary. It will pass near a named star, but not visit it. It may survive for immense spans, but not with guaranteed intact identity. It will lose contact with us, but not motion. So the video resolves into a simple discipline. Ask what kind of travel is being counted. Attach the right boundary to that kind of travel. Do not let one impressive fact swallow the rest. That discipline is useful beyond Voyager. Deep space questions often work this way. The universe gives us layered relationships where ordinary language wants single edges. A good answer does not flatten the layers, it walks through them until the simple question becomes honest. Voyager 1 is the perfect object for that lesson because it is both familiar and extreme. We know its name. We know its origin. We know it was built by people, launched from Earth, and aimed first at planets. Yet its future now belongs to scales where names and origins do not decide the physics. That tension is why the title keeps its pull all the way to the end. It also gives the viewer a way to remember the answer after the video is over. Start near, then move outward. First the working machine, then the radio link, then the silent body, then the heliopause, then the Oort Cloud, then the named star that is still not a destination, then the moving galaxy and the uncertain artifact. The sequence is simple enough to hold clearly after the video ends, but accurate enough not to mislead. That memory path is important because Voyager is one of those subjects where a single memorable fact can distort the whole picture. The cure is not more facts piled randomly on top. The cure is order. Once the order is right, every fact has a place. The stronger answer is not harder to remember. It resists oversimplification, and that resistance is the point and the safeguard. It keeps the spacecraft close enough to care about, and distant enough to teach scale honestly, without turning either side into a slogan. And for a night viewer following the chain quietly, that matters. The answer can stay memorable without becoming false. It can stay precise without losing the human object at the center. Now let the answer settle. Voyager 1 is still moving away from the Sun. That was the first fact. It remains the last fact. Everything else in between has taught us how carefully that motion has to be named. As a living spacecraft, it has a near future. The power supply keeps shrinking. The system keeps aging. Engineers keep choosing what can be preserved and what has to be surrendered. This is the shortest answer and the most human one, because people are still part of it. As a signal, Voyager has a wider but fragile future. Earth may hear it for a while longer if the chain holds. The transmitter has to speak. The antenna has to point. The deep space network has to listen. The delay keeps growing. The relationship becomes thinner, not because the object is less real, but because the bridge between object and home is harder to maintain. As a silent object, Voyager has a much larger future. When the signal ends, the trajectory does not. The spacecraft does not need to report its position for gravity to keep working. It does not need to answer Earth for its path to remain real. As a boundary crosser, it has already done something extraordinary. It has gone beyond the heliopause, outside the Sun's wind bubble, into interstellar space under that definition. But the broader solar story stretches farther. The Oort Cloud scale tells us that leaving one edge is not the same as leaving every possible edge. As a future passerby of Gliese 445, it gives us the most humbling reset. Even after about 40,000 years, the famous stellar milestone is still not arrival. 1.7 light-years is close in one map and enormous in every human sense. As a galactic object, it has no final station waiting in the dark. The map moves. The reference points change. The spacecraft continues through relationships, not toward a destination that completes the story. And as material, it may survive for immense spans, though we should not pretend to know its condition forever. It may remain a recognizable artifact. It may be altered. It may become pieces. The deeper the future, the more the answer moves from distance to persistence. So how far can the Voyager 1 travel? The clean answer is this: not very far as a living mission, farther as a signal, far beyond silence as an object, through the sun's outer boundary regions over deep time, near another star without visiting it, and onward through the Milky Way as long as the object or its remnants continue to move. The mission ends first. The motion does not. That is not a trick answer. It is the only answer that respects the spacecraft. Voyager 1 is not a train headed for a final station. It is a human-made object carrying velocity through layered boundaries, fading relationships, and moving reference frames. A natural next question for this channel is how that rare outer planet road opened in the first place, and why Voyager's launch window mattered so much. But that belongs after this answer, not inside it. For now, the final image should stay simple. A small spacecraft moves outward. Earth listens for as long as listening remains possible. The sun's wind is already behind it. A possible comet cloud waits on a scale that makes centuries feel short. A future stellar proximity waits farther still, and even that is not close in the way our instincts want it to be. Beyond all of it, the galaxy keeps moving, and Voyager moves with it.